Okay. So finally, I think it's time to start. Some people decided to have control of the cake, even though...
No, it's nice and warm.
So, welcome. Quite a lot of people here today. That's great. Today's speaker is Balcells, and he will talk about challenging TD-DFT in catalyst design aimed at water oxidation and carbon dioxide reduction.
Okay, yeah, thanks, Simon. So what I'm going to do in this presentation is to talk about basically two different projects that we started recently during the last year related to these two reactions. So I'm afraid it's not like lots of results that we have already, but I guess it's enough as to show how we are getting started and so which are the future directions that we want to follow. Okay, so I'll start introducing this catalytic water oxidation reaction. This is probably one of the most important reactions that has to be developed to develop carbon-free renewable energy sources based on an artificial photosynthesis scheme. Okay, so this is what we have already, and we can make a small home-scale implementation of this. It's just getting electrical power from sunlight with a photovoltaic device. And then the issue here is that even if we manage to optimize very well the cost efficiency ratio of these materials, then still we have an intermittent source of energy, of course. So it would be nice to, if we can transform and store at least part of this energy so that we can recover it when this source is not available. So one possibility for doing this is to use part of this electrical power to force the electrochemical splitting of water into hydrogen and oxygen. Then if we manage to store hydrogen in a cheap and safe way, which is a challenge itself, we can use the opposite reaction in a fuel cell, hydrogen and oxygen to water, which is then a spontaneous reaction to generate electricity. Okay, the problem with this scheme is that to do this water splitting, we have to oxidize water to oxygen. And that's a very difficult reaction. It is an endoergic reaction. It has a potential which is over 1.2 volts. And then also it has an overpotential, which can be as high as 1 full volt. So it's also a very slow reaction, and therefore we need a catalyst for it. The fact that it's endoergic, it's not a big problem if you find a good way of coupling this reaction to this electrical power or another source of energy. But still you need catalysis. Why it is so difficult? Well, it involves a large amount of redox equivalents, 4 in total, which is a lot. And it requires breaking an OH bond 4 times. And also you have to form an oxygen-oxygen bond. On a chemical system, it's not very difficult to generate an electron-rich oxygen. Oxygen, after all, it's very electronegative. But it's not so obvious to generate an electrophile oxygen and then to do this in an amphiphilic system so that both characters meet. So you have a nucleophilic and electrophilic oxygen that like to get together and form an oxygen-oxygen bond. That's not obvious at all. Anyway, we have this reaction taking place all around us in a gigaton scale. Nature does this, plants do it, through photosynthesis in what is called the photosystem 2, which is this wonderful molecule or system here. Not an easy one, not a simple one. It has a very complicated structure and function, as you can see. But anyway, sunlight is absorbed somewhere over here by a chromophore. There is electron excitation, there's a potential generated which somehow travels to this region here, and then buried somewhere here, it's not really visible in that picture, you have this oxygen evolving complex, which is stabilized by many different amino acids, and that's the one that really does the chemistry. So it contains this manganese cubane structure with calcium and also this pending manganese here. And there are these oxo bridges that actually do this water oxidation chemistry. And then nature uses these reducing equivalents to reduce carbon dioxide to carbohydrates. Well, there's actually still a lot of investigations and debate on the structure and function of this system. It's far from being completely clear, but the insight obtained so far already has been used to develop bio-inspired catalysts like these cobalt oxide cubanes here, are good catalysts for water oxidation. Then we also have completely artificial catalysts that have nothing to do with photosystem 2, and that's the field where we work. So I was actually working for a while with Odile and the experimental group of Bob Curie on these Iridium-3 complexes. So it's an Iridium-3 complex. This 3 means that it's an oxidation state. If you want, it's a formal charge of +3 because we have 3 anionic ligands around it that are supporting this metal center, which is this CP star, this chloride ligand, and this phenylpyridine ligand. So what we found here from calculations and experiments is that we can oxidize this complex to this Iridium-5 oxo cationic complex. Now we have a higher oxidation state, Iridium-5, so more electron deficient metal center that will promote this water oxidation. And the good thing about this complex is that you can do this oxidation reaction with potentials that are below 1.7 volts, which is the limit with cerium ammonium nitrate, which is a stoichiometric oxidant that is used in these experiments to oxidize water. Well then, this Iridium-5 oxo complex actually has a very interesting electronic structure, which is the following. So that, of course, it has a set of pi bonding and pi star anti-bonding orbitals associated to this Iridium-5 oxo moiety. And so here that's a representation for a bonding orbital. That's a metal d orbital on iridium, and that's a p orbital on oxygen. And then there's the corresponding anti-bonding orbital. And of course, there's an x and y set, because there's this orbital and then the one that is orthogonal to it. Fine. So what we found computationally is that in the ground state of this Iridium-5 oxo complex, we have this quite or rather unusual electronic configuration in which the pi orbitals are full, and one of the pi stars is also occupied. As I said, this is quite unusual. Normally what you have is that either all the pi's are full and the pi stars are empty, then you have actually a very stable oxo compound that will probably not be reactive in water oxidation, or you have all the pi and all the pi star full, and then the bond will probably dissociate, will not be a stable species. So here we have a midpoint situation, and that's of course good for this catalysis chemistry. It activates the bond. The bond is destroyed to some extent because one of the 2 pi star levels is filled with 2 electrons. And as I said, that's good for water oxidation, so that's the transition state associated to this Iridium-5 oxo species to make the oxygen-oxygen bond to oxidize water. So we have a molecule of water attacking this oxo group. And then the other good thing about this electronic structure is that the HOMO and the LUMO are very similar. They're both pi star orbitals, therefore they're not only close in nature, shape, and so on, but also close in energy, which means a narrow HOMO-LUMO energy gap, which is always good for reactivity. So that in a way we have a high energy HOMO orbital that is ready to take the proton that we have to remove from water, and a low-lying LUMO that will be taking the resulting hydroxide ion to make the oxygen-oxygen bond. Still, this system has issues, not so nice features. One problem here is robustness. The phenylpyridine, especially the CP star ligand, are prone to undergo oxidation under the harsh conditions that are used to do this chemistry. And that's not a nice feature, of course. And the other problem is that even though having this pi and pi star sort of half occupied in a way, it's a good feature. It's too concentrated over 2 atoms only. So it's not so difficult to transfer the OH minus, but the proton is a bit of a problem. And actually, lowest barrier we managed to found for this key event, which is forming the OO bond, was rather high. 24 kcal per mole was the lowest we were able to obtain. And actually, experimentally, the system is quite slow. Now there are much faster catalysts developed already for this reaction. So then we thought, okay, let's try to dream a bit about what would be the ideal catalyst for this reaction. And so this is the system we're trying to engineer here. It's based on a dinuclear complex that we are trying to develop in collaboration with Curie group. And so why we like it? Why we think it's ideal for water oxidation? Well, because of the following reasons. First of all, it's based on these pyridine alkoxide ligands, which are known to be strong donors, and that's important to stabilize high oxidation states, which is what we need for water oxidation. because it has a lone pair here on nitrogen, and then it has this anionic alkoxide oxygen there. They're also known to be robust under oxidizing conditions, which is good as well. And then they're tunable because you can, for instance, in this pyridine ring, you can introduce substituents and play around with electronic and steric effects. The other nice feature is this syn oxo-hydroxo moiety there, so that it's ideal to get a hydroxide from water and form the oxygen-oxygen bond, and then the resulting proton goes to the hydroxide to form an aqua ligand. Actually, the proton can also come to this bridging oxo here. And that's very important because the third feature we're aiming for there is that this oxo bridge that is connecting the two metal centers actually introduce some degree of cooperation between the two metal centers to reach these cycle-oxidation states by electron delocalization. So the idea there is that if we have to oxidize one of the metal centers a lot to promote this water oxidation, so we have a very electron-deficient metal center, the other will help by delocalizing part of its charge, so from one metal center to the other. But that's all hypothesis, that's all ideas. So then, down to earth, that's what's been achieved so far in the Triplet labs, synthetically. That's the compound that they've been able to synthesize so far, and it's the one in which we are working now. So it's not very far from this, actually. Main problem is that instead of having this fancy oxo-hydroxo feature here, we have chlorides. So they just get into the chloride salt of this compound, which is good in a way. Then it's very stable. They grow crystals of this. We have a crystal structure. And then we hope that under oxidation conditions, this may get into this oxo-hydroxide ideal moiety to oxidize water. But for the moment, we work on this compound. So we optimize the geometry of this complex. And we did this by means of DFT calculations with the pure PV function as implemented in Gaussian 09. We introduced dispersion with the Green model, and we use a triple Z quality-based set with several potentials on iridium to account for relativistic effects and polarization functions on the other centers, and we use an ultrafine grid for higher numerical accuracy. And actually, so we compared this structure, of course, to what we see in the crystal. So here's the PV result. And so we get a root mean square deviation in the distances of about 0.034, which is quite good. And actually we tried different functionals. Of course the pure, which always have the advantage of running faster, which is important in a project like this because we will, at some point when we go for the mechanism, we will need to run quite a lot of calculations, quite many calculations. So you have the VLYP, MO6L, TPSS, and the PV, and then the corresponding hybrids, which are to some extent better, but also more expensive, of course. Also, another interesting feature of this compound is that it has this bend or angular oxo bridge. So this theta angle, it's the angle between iridium, the oxo, and other iridium, so it is this angle up here. So we also looked at the deviation, and in general, the deviations are quite low, below 6 degrees. So we reproduce this angular feature, which is not an obvious one, because normally this band bridge comes from a situation in which a linear bridge will be associated to anti-bonding interactions between the metal d orbitals in the extreme and the central p orbital on the oxo bridge. And then if that is true, what we gain with the bending is introducing in-phase bonding combinations here that of course stabilize the system, and that's a reason why it is actually bent. And we indeed see these in our calculations on the structure of this dimer complex, actually right at the HOMO level for the closed shell singlet state. We can see this overlap upon bending between these p orbital on oxygen and the metal d orbitals, which is not possible if we have a linear structure. So that's quite a difficult feature that gets well reproduced by the calculations. And then we tried with the UVVs. It's always interesting to look at the UVVs of these species if we, at some point, for instance, aim for photocatalytic applications in which we need to absorb light to drive a reaction. So here's how it looks like. So the black line is for the experimental UV visible spectrum, and the one in this sort of orange color is the TD-DFT for the closed shell singlet. Now the TD-DFT, it's done with this omega B97XD functional from the head-cordon group that contains both dispersion and long-range corrections. That's its implementation in Gaussian 09. The reason why we use this functional is that other groups have benchmarked this and proved that this functional is good for many systems. I mean, gives a good agreement with experimental spectra. And the group of Kundari has also used this functional to study UV visible absorption of similar iridium dimers. Of course, we introduce solvation. That's very important for UV visible absorption. We do this with a Truller SMD continuum model for dichloromethane, and then the same basis set an ultrafine grid. Okay, so we are quite satisfied with this band here, that you can easily correlate with this one here, of course, and we're also happy because it is associated to an electron transition from the HOMO to the LUMO that takes place in the near infrared region of the visible spectrum. Means we have a narrow gap there, which is always good. And also we have, both in the HOMO and the LUMO, we have contribution coming not only from this p orbital on the oxo bridge, but also from the d metal orbitals, both in the HOMO and the LUMO, which is suggesting that we actually have these, that the system is bound to have this cooperation between the two metal centers that we were aiming for. However, these features are not so nice. So we miss the shoulder there. It's gone in the calculations, and the secondary line is quite blue shifted. So there's something going on there, probably. Okay, so then we started thinking about other possible electronic states for these species, and then, okay, if we do all the electron count and stuff, we will realize that actually this complex is an iridium-4 species, so which means that formally we can think that it is D5 here and D5 here, and therefore we can have an unpaired electron on each metal center, which may couple in a parallel ferromagnetic way, so that overall we have an open shell triplet. Since now everything you've seen, it's a closed shell singlet solution for this system. Okay, so this actually converged. It yields minimum in the potential energy surface, and here's how the spin density of these species looks like. So we have a spin density on both metal centers, so the alpha goes in blue, the beta spin density goes in green. So there's clearly localization of the spin density on the metal centers in a ferromagnetic parallel way, and on the oxo as well. That's very nice. We're not expecting this, so we have oxyl character here. This means that this molecule, this system can also be interesting, or might be used for CH oxidation reactions, because oxyl means an oxygen with radical character, typically promote these reactions. They promote the homolytic cleavage of CH bonds, so you can think methane oxidation to methanol, for instance, which is also a highly regarded reaction. Okay, then we also looked at, again, we compared with the crystal structure. And what we see is, so here you have PV and PV0, so pure and hybrid functionals, and I'm giving data for the closed shell singlet, that's what the CSSS mean, and the open shell triplet, the OST state, right? So in terms of root mean square deviations, whatever the functional you use, they're quite similar, low deviations, but then there's something going on with this angle between iridium, oxygen, and iridium. There's a large variation for the triplet state, a large deviation. Why is that? Because now the structure is not angular anymore, but linear, and we believe that this is to promote the exchange between the two parallel and paired electrons, which would compensate for those anti-bonding out-of-phase combination between the orbitals. So there's a disagreement there. And then even more, the UV visible doesn't look very nice. So now the main absorption shifts, blue shifts. It kind of matches this one, if you want, the shoulder there, but not really, because it actually has a high intensity compared to the closed shell singlet state. And the shoulder, as you can see on the experimental, which is given in black here, goes at low intensity. So not matching really. And then also for the secondary line, again, it's blue shifted, and it's actually more blue shifted than it was for the closed shell singlet state. Then they actually ran some extra experiments, and what they found is that, so they have NMR, API, and SQUID data, and all these data point towards a diamagnetic species. So probably this open shell triplet state is not relevant at all. It's not there, it's not stable. Okay, so then we thought...
What is the energy of the open shell triplet?
What's that?
What is the energy?
Yeah, well, that will come later. Okay, so Yeah, that's of course an important feature. Okay, so what we got from here actually though is that we can take this spin and kind of concentrate it or locate it on these metal centers and the oxide. Right, good. So then we thought what we can try to do is to spin flip on one side and not on the other, so that instead of having a parallel spin ferromagnetic solution, we have an anti-parallel anti-ferromagnetic solution to this, and for that we need to do broken symmetry DFT. So we are going to break the spin symmetry, and so we will look for a solution that has an alpha spin orbital that is shifted or localized on one side, on one of the two metal centers, whereas on the other we will locate a beta spin orbital. Yeah, that's the 2D picture of this, right? So that was quite pain in the neck because Gaussian 09 is not really optimized to do this kind of calculation, so it is difficult. You have to play around the tricks, but we finally got it, and that's how it looks like. So it converges as a minimum in the potential energy surface, and this is how the spin density looks like. Again, alpha and beta spin density, blue and green. So now we have a spin up here on this metal center, spin down here on this other metal center, and we go back to an angular geometry because we don't have this exchange anymore between parallel spins. This is how the agreement to the crystal structure looks like. Very good. So this is PV, closed shell singlet, open shell singlet. Basically they agree the same. The RMSD for the distances is the same, and very similar deviation in terms of this angle. So looks good. Looks like this open shell singlet is relevant, and even more than from the UV visible spectrum because, okay, so here again is in black the experimental one. And then nice features here is that now this main band is losing intensity, it's going down, and it correlates very well with the shoulder. And then the secondary one also gets very well aligned. And then of course the problem is here. This one is gone. Okay. So that was our hypothesis for this system, is that most likely we have a multi-reference singlet state here, ground state. Einar was asking for the energies, here they are. So this is closed shell singlet, open shell triplet. And they are in kcal per mole. And of course this should be wrong. This is wrong for sure. It cannot be that the triplet is at that energy, I mean just by a thermal population then it should be visible on the experiments, and it is not there. So our hypothesis is that actually these two states, or these two different electronic configurations for the singlet state, mix into a multi-reference singlet state that is stabilized by non-dynamical correlation, so that we end up here significantly lower in energy with respect to the triplet, and therefore the triplet is not visible in the experiments. And this is actually supported, in a way, by the TD-DFT calculations, because if you mix the closed shell and the open shell singlet TD-DFT spectra in a 1-to-1 ratio, which is consistent with these two states being almost degenerate, then we got the best agreement we got so far between the experimental UV visible, which is, as in all the slides, shown in black, and the TD-DFT, which appears in blue here, mixing the two states, or the two electronic solutions, closed shell, open shell for the singlet state. Okay, so ongoing on future work on this, one obvious thing to try is to do multi-reference CAS-SCF and or CAS-PT2 calculations to prove this point, this hypothesis. VMRG, which is this density matrix renormalization group approach, which promises an automated calibration of the active space. It's yeah, seducing or interesting opportunity, at least on paper. But I'm a bit reluctant about doing this because I'm not sure the insight we'll get from this will tell us much more than what we got already from TD-DFT. The other problem is that the system might be too big and complex for this level of calculations, I mean to be done in a reasonable amount of time instead of making a full PhD of it. And then one possibility, of course, is think about the small model. But smaller models are always a bit risky because they should keep the essential features or properties of the real system. So I guess still thinking about this. But of course it will be very nice if we can do it because it will give further support or not support, contradict our hypothesis based on TD-DFT. So More things we want to do is explore lower, higher, and mixed oxidation states. Everything you've seen is for the 4-4 oxidation state complex, but we want to explore 3-3, 4-5, and 5-5. Actually, already got some experimental results there, and we started the calculations there. The nice thing of mapping all these possible oxidation states is that then you can derive redox potentials that can be also compared with experiments and get insight from the calculations. Of course, we also want to get barriers for the O-O bond formation event with this catalytic system. And then also I'm planning for a research stay at UC Berkeley at the group of Don Tilley next spring to start a project on cobalt oxide manganese Q veins that are inspired on the photosystem too, which are also, look also very promising, as very promising systems for water oxidation. Ainar is actually also going to join in this research stay, although she will be in a different group doing different work, which actually relates to the second part of my talk, and also relates, of course, to her FreePro project, which is carbon dioxide reduction. I also start with a brief introduction to this. So what we want to do in this project is to develop catalytic systems for the photocatalytic reduction of carbon dioxide. And we want to do this with functionalized molecular organic frameworks. So I'll start introducing what a MOF, a metal organic framework, is. So it is a nanoporous material that builds upon this unit cell that we can describe as this octahedral feature that on the vertices has metal inorganic compounds that are connected one to the other with some organic molecule that acts as a linker. So that then in here we have a nanoscale or a nano-size pore in which we can introduce a substrate to then do chemistry if we manage to functionalize this with a catalyst. So one of the most interesting examples of these materials is shown here. They're known as UIO 66 and 67. So this metal inorganic compound is this zirconium oxo-hydroxo cluster, and then they're linked with these para-substituted carboxylate ligands that can have one or two phenyl rings. So if we have one phenyl ring, we have the UIO 66, which is the one that is represented here. And we have two, it's the UIO 67 then, which is a bit bigger in terms of pore size. So here in this representation, you can see the zirconium cluster is this feature here. Here are the linker. And then these orange and green spheres represent the pores. And then, as I said, the UIO 67 grows with one more phenyl, and therefore everything is a bit bigger, one phenyl bigger. Okay, so what we want to do with these MOFs, we want to work on the UIO 67 and modify it by replacing this biphenyl structure with a bipyridine, so that then the nitrogen, the lone pairs on nitrogen, can be used to coordinate a photosensitizer. And we started aiming for these ruthenium complexes that are very well known as photosensitizers. So what this molecule is doing is absorbing light in the visible region, and so that creates an electron excitation, and that generates a potential that hopefully will get reducing equivalents from hydrogen that can be then transferred to carbon dioxide to generate formate, or even better, but then even more difficult, methanol. Okay, so this is, I would say, a project on its infancy. The obvious starting point, and what Eirik Thoresen, PhD student in the catalysis group under the supervision of Mats and Mamo, has already started doing, is to synthesize modifications of this photosensitizer ruthenium complex in order to use it as a linker in a MOF. So what you have to do, so it is this decationic ruthenium compound with these three bipyridine ligands. You introduce these carboxylic groups here, so that then you can go to the carboxylate and then bind it to the zirconium clusters and then construct a MOF, so that the MOF will be growing in this direction. And then he tried variations of this. First thing we tried is to replace this nitrogen here by an anionic carbon, so that overall now we have a 1+ molecule, not a 2+. We hope with this that actually the HOMO energy will rise more, that actually the LUMO will go down, so that we redshift the absorption, which is what we want, low energy absorption. UV and near UV absorption, it's always a bit risky it can trigger decomposition processes, and that's not what we want, of course. Then the other thing he did is to move this anionic position to the ligand that grows in the direction of the MOF, that has the carboxylate substituents. And then this is, I guess, a bit of an outside. I will not talk much about this. There are much more modifications here. And also then the MOF grows in a different reaction. What I understand is that the idea is to use this to introduce defects on a MOF. Okay, so IRIC did all the hard experimental work to get all these 4 complexes synthesized and characterized, got the UV visible spectra of them. Here they're given. All the green lines are for the experimental spectra, and lilac, I guess, is for the TD-DFT, which is the calculations that I did. It was quite difficult to get good agreement for these complexes. Now this omega B97XD is not working so well anymore. Actually, it does an excellent job for the UV and near UV absorptions, but it's quite good for the near infrared absorptions. So then what I did, was to benchmark lots of different functionals, like 10, 12. And the M11L, as implemented in Gaussian 09, was found to give the best agreement for the near infrared region, which after all, well, actually the whole visible region, which after all, it's the region in which we are really or most interested. Now the solvent is methanol, which is also introduced with the SMD continuum model, triple Z quality basis set with pseudo potentials and ultrafine grid. Well, the agreement is quite good here. Not so good there, but we fixed that one. I will finish my talk with that one. And I'm not going to talk on this one. But of course, at some point, this is a bit boring, just to reproduce experimental data. But so what's really useful and nice from this TD-DFT calculations is that, for instance, in this case, in which we managed to reproduce the experimental feature quite well, of course, we can get the electron excitations. And that's really interesting. Why is that? Because, well, from the TD-DFT calculations, of course, you cannot know that from experiment. I know that these are the electron excitations that yield these absorptions, so that in the near UV, I have this HOMO -1 to LUMO +7. This central most intense one, it's HOMO -1 to LUMO +1. And then this near infrared one is HOMO -2 to LUMO. And actually, this last one is very interesting because it's the low energy, or lowest energy, goes to the infrared side of the spectrum. And also it has a very interesting nature because it is a transition, it is a metal to ligand charge transfer in which you have one electron excited from this d orbital on ruthenium to this pi star antibonding orbital on the ligand. That's a real important thing. On the ligand that has the carboxylates, and therefore is the ligand defining the direction along which the MOF is growing, so that by doing these electron excitations, we are injecting electrons into the MOF itself, which is the target, of course. And so now, of course, we can start from here. You can speculate modifications, for instance, introducing electron withdrawing groups within these rings that will lower this energy level even more, so that this will be even more infrared shifted. The other thing is that, okay, we come back to this. As I said, we're not very happy with these two cases, but we managed to fix this one. So what was going on there was the following. Of course, the other thing that you can use is TD-DFT calculations, it's to assign structures. And so in this case, we started assuming that we got this cis isomer. So this cis means that this carbon here is in cis position with respect to the carboxylated ligand. And so here's the experimental, which is what it is. There is a single spectrum, of course. And that's what we got TD-DFT for the cis isomer. Not very good agreement, so not too bad here, not too bad here. But in this region, there's a shift of about 50 nanometers, which is a lot. So then we thought, okay, perhaps we have the other possible isomer here, which we call the trans, which just means that now the carbon. So if I do this, I'm just exchanging these two positions, okay? So now the carbon is trans to this carboxylated ligand, and now there's a much better agreement between the TD-DFT and the experimental spectra And this feature was indeed confirmed by the crystal structure, so that when they were able to resolve the crystal shows that the carbon is here in transposition with respect to this carboxylated ligand. Okay, so with that slide I finish. So ongoing and future work related to this carbon dioxide reduction is to, I would say I'm still not fully satisfied with the agreement between theory and experiment for the UV visible. So I guess we have to think about the method. I don't know, perhaps a different implementation of TD-DFT in another software, or perhaps think about the model. But the model, I've been discouraged on this because I tried models with explicit molecules of solvent and ion pairs, because these are charged species, and of course there's always an ion pair around. But really it just makes the calculation more expensive. And this is a bit critical in these projects because, as I said, when we go for the mechanism, then you need to run quite many calculations. And it did not improve the agreement either. So there's something with this, especially with these ruthenium photosensitizers, at least when they have these carboxylate substituents. More things we want to do is explore substitution on the aromatic rings. So yeah, try to develop other linkers, more linkers, then see how this electron excitation actually couples to these zirconium clusters, if there's any coupling. And that, of course, relates to the photocatalytic mechanism involved in doing this carbon dioxide reduction with a MOF. And then, of course, when I switch from this iridium water oxidation chemistry to this carbon dioxide reduction chemistry with MOFs, we switch from sort of molecular systems to materials. Now, of course, these materials have many properties that are quite local, like, say, reactivity. And I think we can model these very well. If we benchmark well the methods and the models, I think we can do a very good job with molecular models. But still there are properties like, say, the size of the pore and how these depends on how you functionalize your linker that, of course, require, call it, periodic DFT. So periodic calculations on the whole thing, on the material, right? And so that's what Einar is going to try in the headquarters group in Berkeley soon. Yeah, if we're given the visa to go, of course. So with that, I want to finish. Thank your kind attention, and I'll be happy to take your questions. Yeah. Thanks.
Thank you very much.
Welcome.
Yes, there's time for some questions. Maybe we'll start here in Oslo. Okay, so I will change the camera to okay, Michele?
Yeah, I have more a comment than a question. Regarding the trisbutyrridine, routine trisbutyrridine, okay, there has been, you have methanol as solvent. There have been studies on water, the system in water, where they've shown that the 3-butyridine form grooves, and you have solvent that water enters in the grooves. And the electrostatic dipole of the water in these grooves is directly coupled to the electronic state in the excited states.
Yep.
And then they form asymmetries that destroy completely the spectra that you have in the optimized geometry.
Right.
And moreover, they stabilize polarization in the excited state.
Right.
So, for example, in the triplet state, you have that. If you just compute the symmetric structure, you expect that the exciton goes on the whole molecule. But because of the coupling with the solvent, you have that actually the exciton localizes in one of the 3-butyridine.
Right.
And solvent dynamics, you have that the exciton moves in the structure. So I think this is why probably if you take just a explicit solvent calculation, maybe one or few snapshots are completely off because they don't make sense.
Right.
They make sense only on a very large sample.
On
the other hand, I mean, if you have this coupling and you have asymmetry, because you have intrinsic asymmetry with the MOF, this is something that you could design on the right way to force the excitation going in the right direction.
Yeah. Yeah, that's a good point. Yeah, I agree. It's probably an important factor that we should take into account in the modeling. Yeah. What we've done so far, it's just this continuum solvent modeling. These are, of course, a static calculus. It's quite an approach in many ways. And then there, so we see what happens with the omega B97XD functional then is that the near infrared region of the spectra actually appears blue shifted. And then if we then use mixed models in which there is both solvation modeled as a continuum and then explicit molecules of salt, but still a static calculation. We don't sample different configurations. Then there is some blue, there is some red shift, so that the agreement improves, but it's very minor. Like we have deviations of 30, 40, 50 nanometers, and then this shift it's like 5 at maximum, and the calculation becomes way more expensive. So, yeah, I guess one thing, yeah.
Take what I said with the grain of salt, because what I know is with water, which is
right.
very different from metal.
Yeah.
On the other hand, if you have solvent that enters into the groove, it's most likely you have a direct dipole coupling.
Yeah.
And then everything you compute with an implicit solvent model might really have major deviations.
Yeah. Right. Good. Yeah. Siemens,
Okay,
right,
so,
I guess.
There's a short real question. That is, have you tested the sensitivity of the choice of basis sets towards the stability of the spectra you get?
I don't think so. Perhaps could be. Perhaps I should try a quadruple Z quality or even quintuple Z quality basis set, and perhaps will improve the agreement. That could be. Yeah.
Also the core size of the solar potential.
Well, these pseudo-potential basis sets we're using, they're already small core. I'm not sure they're even smaller cores than those, but perhaps we can also try a full electron basis set. But I'm not sure that. I guess I've not tried this because people trying benchmarking, they're kind of ignoring the basis set. I hope they do it for a good reason. I don't know. In principle, they're more experts on that than I am, so I don't know. Yeah. So it's worth trying, perhaps, yeah. Use smaller core if available, and then quadruple or even quintuple. After all, it's basically a single, well, it's a bit more expensive than a single point calculation, but not much more. So, yeah, perhaps it's a direction to explore.
You go?
Yeah, you didn't seem to concern with intensities. I guess they are not very well reproduced by the method. And also a little bit.
But there's a problem there.
What would be the intensity of, for example, the highest,
Well,
of the 5 to the lowest?
Yeah.
The 5, they did not appear at all in your.
Well, when I deconvolute the spectra, when I translate my Gaussian data into these lines here that are adjusted with Gaussian functions and so on, the intensity is there, so it is taken into account. And that, but like in general,
You get the intensities out, so those are used here.
Yes. But the general trend, but there's an interesting point there, which is the general trend. If you look basically at all our spectra that I've shown, whatever it's the Iridium system or the Ruthenium system, the experimental one always goes below. Then I guess one reason for that is that this is absorbance, so it means that you take your molar absorptivities and then multiply that by the length of the cubate and then your concentration. Then, of course, not everything you put in there that you dissolve, that is your sort of theoretical concentration, might not be there, all of it. I mean, part of the metal species that you're introducing might be yielding other compounds that perhaps may not absorb, or you see what I'm saying there? I mean, not everything you dissolve and then record is necessarily doing the absorption, is necessarily that complex, might be other complexes that do not absorb. And I think that's the reason why our predictions always go in intensity, they always go above experiment. But that's an hypothesis, I don't really know.
One of the last slides, you had sort of different excitations.
Yeah, the excitations here, let's see, yeah, I have this here. See if I find it here. Right, yeah, so these lines here are scaled with the intensity.
So,
well, actually they're drawn.
The homovolumia has no intensity.
Yeah, that's a good point. Because it's a forbidden transition because of symmetry reasons? I guess so. I don't know. I have not looked at that in detail. Yeah.
Okay, almost.
Yeah, I have one question which is perhaps a little naive, I don't know, and then a suggestion. The question is, how reasonable is it to compare gas phase structures to crystals?
Oh, that's a good point. It's good. It's reasonable if crystal packing effects are not very important. And then normally crystal packing effects are dispersion based, and I mean, they do not normally show very high. I mean, the main problem when comparing this is that, for instance, here, when you have counter-ions, of course. So when you have something like this on your unit cell, of course, then you have, so this overall is a cation, and then this feature here, I guess this is PF6 minus, right? It looks like that. I guess it's PF6 minus. Of course, that is polarizing this ring down here, and then, of course, then when you do the gas phase calculation of this for the cation without this, of course, there will be some deviation there. But this is normally minor. Yeah, but it can be, yeah, it's something to take into account. But then, you know, the problem is what you compare with then. There's some people who try to sort of derive dielectric constant for a crystal, and then you can do, you know, just use this SMD model and use a dielectric constant that resembles that of the crystal. That's a possibility. But I don't think this is very important, at least not on the systems we do or we are studying currently. But it can be an issue. It's something you have to, yeah, keep an eye on it, especially when you have a lot of charge. So I can tell that in a few systems we've got problems, and then we rather try to optimize the ion paired system when you have 3 plus versus 3 minus. So when there's a lot of charge separation, then of course, then it is an issue. But if it is a neutral species or it's only 1 plus, 1 minus, normally it's fine. Yeah.
The suggestion is this. We just, we have, now it's in the development version of the MOLCAS, but we actually implemented the DMRG there. And then we coupled it to the Cholesky stuff I did in there, and then the computation time went from 5 days to about an hour.
Okay, that sounds interesting.
So maybe we should have a look at
trying
that out.
And metals are doable.
Well, I mean, of course.
Yeah, well, they're not in all codes, but okay.
MOLCAS is supposed to be for lanthanoids and actinoids. Right?
Very good. Yeah, then it's not a problem there. Fine, good.
Okay, so one final question.
You are benchmarking the functionals when comparing them, making a comparison between experimental length and angle.
Yes.
But what about there are many differences between changing when you change the functional, the UV visible spectra changes a lot?
Well, for Iridium, we did not benchmark the method for the spectra, but for the crystal structure.
Yeah.
And the reason why we did not re-benchmark for the TD-DFT in the UVs is that basically because of work of Kundari on similar complexes, work of a group led by a guy called Tom Kundari. Okay, and then we were happy with the agreement there, but then it was kind of the opposite with the ruthenium project. In there, I mean, of course, when we switched to M11L for the spectra, because we found the best fit, then of course we rechecked that M11L was also giving good crystal structures, which was the case. But then, of course, you can get into a problem because it may happen that perhaps there's a functional working very well for the crystals, but then a different one working very well for the TD-DFT. I guess it can happen. I don't know. It did not happen here, luckily enough. Yeah.
But the differences are very, very big, or?
You mean for the TD-DFT?
Yes.
Yes. Yeah. Well, can be huge between different functionals. Yes. But I mean, my impression is that there are functionals that are good. When if you think virtual orbitals, there are functionals that are very good at the HOMO-LUMO level, so close to the LUMO if you want, and then you get the near-infrared region very well. That happens with the M11L functional, for instance, whereas there are others that get very well the energies of the higher virtual orbitals, and then you get a good agreement on the UV, near-UV region. But apparently it's difficult to, really did not find any functional that has a good balance between the two regions. Or that's been our experience so far.
Okay, great. So are there any questions from Tromsø?
No, there doesn't seem to be.
Okay.
Oh, sorry, one question.
Okay.
I need this
microphone. Oh my God. See if I understand something.
Okay, I wonder about the physics behind this, because I suppose you are going to judge a lot of charges which are moving around in the systems, and you are going to excite phonons and also plasmas in the system, and also in the solvent around it, it will be charged. So it means that you have very dominant excitations. Do you take that into account somehow with kind of things, or what do you do?
I'm not sure I understand your question.
Well, it's not, if you charge the system by,
If you charge the system, yeah.
by exciting it to ions, and you
Yeah,
can move around
has,
these electrons.
It has an influence, of course, whether you have a +2 or a +1 system has a big impact on your excitations, like at which energy they're happening, of course. And actually, I would say that the trend we see there, that the larger the charge, the more difficult it is to reproduce the experimental spectra, probably because, for instance, ion pairing interactions become more important. But there's, yeah, certainly an influence of that feature. And I would say it's not easy to model or reproduce, but
No, it's not easy.
yes.
That's the point, I guess, because it's not the charge, it's a dominant process in the system, I think.
Yeah.
Okay.
Okay, so then I think our time is up at this time, and I thank David Balcells once more.
Thanks.